Welcome to Daikin Web-Based Training. Today, we will learn the pH chart and the coefficient of performance. Before beginning with the main focus, I would like to touch upon the relationship between the coefficient of performance and global warming. Electricity is an essential element of our social infrastructure today, and its use has an impact on global warming. Therefore, it is important to improve the operating efficiency of machines. In other words, to promote higher energy efficiency in order to prevent global warming. Coefficient of performance, abbreviated COP, is a measure used as the standard for energy efficiency in air conditioners. The COP level is listed in product catalogs and the like, serving as one of the factors users consider when purchasing air conditioners. COP, however, is condition-specific and can change according to the operating conditions of the air conditioner in question. The operating environment and actual usage of the air conditioner can result in inefficient operation. We can use the pH chart to examine the optimal operating conditions for energy efficiency by looking at the COP. Let's go over today's topics. We will learn how to calculate the COP using a pH chart and examine what optimal operation is based on the COP, taking several operating conditions as examples. Now, what is the meaning of the COP? As it is a measure of the air conditioner's operating efficiency, it is used as a standard for the energy efficiency of these machines. For example, the COP of an electric heater is 1. This means that 1 kilowatt of electrical power must be consumed in order to achieve 1 kilowatt of heating capacity. Meanwhile, air conditioners are energy-efficient systems with a high COP. The COP of electric heaters and air conditioners is called device COP and denotes the ratio of heat transfer capacity to consumed power in the entire device. This COP can be found in product catalogs and other related materials. The COP we will be focusing on today is called cycle COP and denotes the ratio of heat transfer capacity to consumed power by the compressor. This COP can be calculated using the pH chart. There are two types of cycle COPs, the refrigeration cycle COP during cooling operation and the heat pump cycle COP during heating operation. Let's begin with an explanation on how the refrigeration cycle COP is calculated. In order to calculate it, the refrigeration cycle must be drawn on the pH chart, which requires the 4 pieces of air conditioner operation data mentioned on the slide. These data allow you to depict the refrigeration cycle as shown here. This refrigeration cycle is also called the theoretical refrigeration cycle, which is different from the actual refrigeration cycle. We will explain the difference later. First, I would like to explain how to calculate cooling capacity from the theoretical refrigeration cycle on the pH chart. The evaporation process is represented by the changes within the cycle from 4 to 1. The change in specific enthalpy, H1 minus H4, is referred to as the refrigerating effect and represents the quantity of heat absorbed by 1 pound of refrigerant. The volume of refrigerant flow within the cycle is referred to as the refrigerant flow rate and expressed in volume per unit of time. And the cooling capacity can be calculated by multiplying the refrigerating effect by the refrigerant flow rate. Now I would like to explain how to calculate the energy consumed by the compressor. The compression process in the theoretical refrigeration cycle is represented by changes on the constant entropy line from 1 to 2 and is referred to as the theoretical adiabatic compression. The change in specific enthalpy H2 minus H1 is referred to as the theoretical adiabatic compression work and represents the work required to compress 1 pound of refrigerant in this process. Multiplying this value by the refrigerant flow rate gives you the compression work per unit of time, which is referred to as the compression power. In other words, the compression power represents the energy consumed by the compressor. Based on the above results, we can calculate the COP for the theoretical refrigeration cycle. It is represented by the ratio of the cooling capacity to the compression power and is calculated as follows. As you can see from the formula, even if the refrigerant flow rate is unknown, the COP can be calculated by reading the refrigerating effect and compression work from the refrigeration cycle on the pH chart. Now, I would like to explain how to calculate the COP for the theoretical heat pump cycle. The condensation process is represented by the theoretical heat pump cycle from 2 to 3. The amount of change in specific enthalpy, H2 minus H4, is referred to as the condensing load and represents the quantity of heat discharged by 1 pound of refrigerant flowing through the condenser during this process. This heat quantity is equal to that of the refrigerating effect and compression work in total. Regardless of the refrigerant flow rate, the COP can be expressed by a ratio of the condenser duty to the theoretical adiabatic compression work. Moreover, as this formula shows, the theoretical heat pump cycle COP can be found by adding 1 to the theoretical refrigeration cycle COP. However, it is applicable when the conditions are the same for each cycle. Now let's take a look at the difference between the theoretical and actual refrigeration cycles. The difference is found in the compression process. Unlike the theoretical adiabatic compression process, the actual compression process does not change on the constant entropy line. This is because the resistance against the refrigerant vapor and the energy loss due to mechanical friction within the compressor are absorbed by the refrigerant as heat. This effectively increases the specific enthalpy of the compressor discharge point and raises the temperature. In addition to the 4 pieces of operation data, one other piece of operation data in the form of the compressor discharge temperature is required in order to depict the actual refrigeration cycle on the pH chart. Using these 5 pieces of data, we can depict the actual refrigeration cycle as shown on the slide. Let's compare the actual and theoretical refrigeration cycle COPs. The formulae for these 2 COPs are as shown on the slide. The actual compressor discharge point differs from the theoretical point, making the actual compression work larger than the theoretical adiabatic compression work. As a result, the actual COP is smaller than the theoretical COP. To this point, I have explained how to calculate the COP using the pH chart. Now, let's use what we have learned to examine the optimal operating conditions for energy efficiency. We will do this by using an air-cooled air conditioner running on R410A as our model and randomly altering the data within its standard cycle in order to compare the respective theoretical refrigeration cycle COPs. Here is an explanation of the patterns of alteration and their conditions. Pattern 1 mentions that condensation temperature is 9 degrees Fahrenheit higher than the standard. Pattern 2 mentions that condensation temperature is 9 degrees Fahrenheit lower than the standard. Pattern 3 mentions that evaporation temperature is 9 degrees Fahrenheit higher than the standard. Pattern 4 mentions that evaporation temperature is 9 degrees Fahrenheit lower than the standard. The detailed operation data for each pattern are as shown on the slide, with the superheat and subcool temperatures both the same as the standard at 9 degrees Fahrenheit. The refrigeration cycle can be depicted on the slide using the operation data for the standard cycle. As mentioned before, the refrigeration cycle, COP, is the ratio of the refrigerating effect to the compression work. The refrigerating effect and compression work are differences in specific enthalpy, respectively H1 minus H4 and H2 minus H1. Therefore, the COP for the standard cycle is calculated as 4.08. Let's examine the COP for pattern 1. The operation data is shown on the slide. It is an alteration of condensation pressure to a higher level than that found in the standard refrigeration cycle. The conceivable scenario in this case would be insufficient heat exchange within the condenser due to reasons such as a high outdoor temperature or contamination of the condenser. The refrigeration cycle can be depicted on the slide using the operation data for pattern 1. The pH chart shows that compared to the standard cycle, the refrigerating effect is smaller and compression work is larger for pattern 1. Therefore, the COP for pattern 1 is calculated as 3.44, which is 15% lower than the standard cycle COP, indicating poorer operating efficiency. Now let's take a look at pattern 2. It is an alteration of condensation pressure to a lower level than that found in the standard refrigeration cycle. The conceivable scenario in this case would be a better heat exchange within the condenser due to reasons such as a low outdoor temperature or when water is sprayed on the condenser. If we depict the refrigeration cycle on the pH chart and compare it to the standard cycle, the refrigerating effect is larger and compression work is smaller for pattern 2, resulting in a COP of 4.85. This is 20% higher than the standard cycle COP and indicates efficient operation. In pattern 3, we will examine the influence of the evaporator. The operation data is shown on the slide. It is the alteration of evaporation pressure to a higher level than that found in the standard refrigeration cycle. The conceivable scenarios in this case would be a high set room temperature or improved heat exchange within the evaporator. Compared to the standard cycle, the refrigerating effect is virtually the same and the compression work is slightly lower, resulting in a COP of 4.75. This is approximately 20% higher than the standard refrigeration cycle COP. Let's take a look at pattern 4. It is the alteration of evaporation pressure to a lower level than that in the standard refrigeration cycle. Conceivable scenarios in this case would be a low set room temperature or insufficient heat exchange due to contamination of the evaporator. Compared to the standard cycle, the refrigerating effect is virtually the same and the compression work is slightly higher, resulting in a COP of 3.66. This is approximately 10% lower than the standard refrigeration cycle COP. These results show that the operating conditions that would contribute to higher energy efficiency can be seen in patterns 2 and 3. It it is important that the evaporator and condenser not develop insufficient heat exchange due to contamination or short cycling, and the set temperature not be lowered unnecessarily. In other words, operating without the condensation pressure too high and evaporation pressure too low will effectively increase the COP. Finally, let's take a look at the COP when evaporation pressure is high and condensation pressure low. In this case, it is important to avoid heat exchanger contamination and insufficient heat exchange from short cycling due to poor installation. Also, ensure that the room temperature is set high to increase evaporation pressure and that the condenser is sprayed with water intermittently to lower condensation pressure. This results in a higher refrigerating effect and smaller compression work compared to the standard cycle, bringing about a COP of 5.72. This is a 40% higher COP than the standard refrigeration cycle and the highest COP compared to the previous 4 patterns. In other words, the optimal operating condition for energy efficiency features a lower compression work and a higher refrigerating effect. Therefore, it is important to install properly, maintain regularly, and make careful considerations when using air conditioning equipment.